Hi everyone. Today we will be starting differential calculus. In today's session we will see limits, continuity, differentiability and mean value theorem. So let us first start with limits. A number L is said to be limit of function fx as x tends to a if for any arbitrarily chosen positive integer epsilon greater than 0, however small, there exists a corresponding number delta greater than 0 such that fx minus L is less than epsilon for all values of x for which x minus a is less than delta, or limit x tends to a fx is equal to L. Okay, so graphically you can show this as, if this is x, this is y, okay, and there is L here and there is a here, okay, and if a plus delta is this, a plus delta and a minus delta, and here this is L minus epsilon and this is L plus epsilon, okay. And this is fx okay. So if x approaches a from left, that is from smaller values of x than a, the limit of f is called left hand limit, okay, and is written as limit x tends to a minus fx is equal to limit h tends to 0 f of a minus h, okay. Similarly, if x approaches a from right, that is from larger value of x than a, the limit of f is defined as right hand limit, okay. So this is left hand limit and right hand limit. X limit x tends to a plus fx is equal to limit h tends to 0 f of a plus h. Okay. So if both right hand limit and left hand limit of f as x tends to a exist, if both left hand limit and right hand limit as x tends to a exist and are equal in value, then the limit of function exists. Okay. If however either or both of these limits do not exist, the limit of f as x tends to a does not exist. Yes or no? Okay. So we can write this as when limit x tends to a plus fx is equal to limit x tends to a minus, or right hand limit is equal to left hand limit, then limit x tends to a fx is equal to limit x tends to a plus fx is equal to limit x tends to a minus fx. So limit of a function can be any real number. Limit can be any real number, infinity or minus infinity. Okay, so infinite or plus infinity or minus infinity are also allowed values for limit of a function. Yes. So let us see this with an example. So for example, if we have to find limit x tends to a 1 by x minus a. So this is a function. So limit x tends to a minus, let us find left hand limit first, or limit h tends to 0, f of a minus h is equal to 1 by a minus h minus a, which is minus 1 by h. Similarly, for right hand limit, we have limit h tends to 0, f of a plus h is equal to 1 by a plus h minus a, so which is 1 by h. So here this was left hand limit, this was right hand limit. So we see that left hand limit is not equal to right hand limit, so limit does not exist. Okay. Next is properties of limits. First property is the limit of a function, if it exists, is unique. Okay, the limit of a function, if it exists, is unique, right? So if second property is if limit x tends to a fx f1x is L1 and limit x tends to a f2x is L2, then limit x tends to a f1x plus f2x plus minus f2x is equal to L1 plus minus L2. Okay, and limit x tends to a f1x into f2x is again L1 into L2. Also, limit x tends to a, f1x by f2x is equal to L1 by L2, given that L2 is not equal to 0. Okay. Fine. So, there are some useful results in limits. So, these are the useful limits. Results. So, you must remember these formulae. Okay. So, next is indeterminate form. See, I will be sharing these notes on my Telegram channel. So, you may find these notes there. Okay. So, next is indeterminate forms. Okay, so indeterminate form 1. If it is 0 by 0 or infinity by infinity form. So a fraction whose numerator and denominator both tend to 0 as x tend to a, say fx, x tends to a becomes 0, and also limit x tends to a gx becomes 0, or limit x tends to a fx becomes infinity, and limit x tends to a gx is again infinity. So then limit x tends to a fx by gx is equal to limit x tends to a f dash x and g dash x. Okay, so here we used L'Hospital's rule. So use L'Hospital's rule. Okay, so what we did, if the limit of fx by gx as x tends to a takes the form 0 by 0, 0 by 0 or infinity by infinity, so differentiate the numerator and denominator separately with respect to x and obtain a new function f dash x by g dash x. So now, as x tends to a, if it again takes the form 0 by 0 or infinity by infinity, again differentiate the numerator and denominator with respect to x and repeat this process until the indeterminate form is removed and we get either a real number, infinity, or minus infinity as a limit. Okay. So let us understand this with an example. So say we have to find limit x tends to 0 e raised to the power x minus 1 plus x squared by 2 whole divided by x cube. Okay, so if you put x is equal to 0, here this is 1, again 1 plus 0 is 1 by 0, so this is in the form 0 by 0. So applying L'Hospital's rule, okay, so limit x tends to 0, after differentiating, if this is fx by gx, So we need to find f dash x by g dash x, okay, is equal to, so differentiating this, we are getting ex minus 0 plus 1, so 1, and plus 2x by 2, that is x, so x, right, and differentiating x cube, so this is 3x square. So again, if you put x is equal to 0, this is again in the 0 by 0 form, right? So let us differentiate this once again. So limit x tends to 0 f double dash x by g double dash x, which is e raised to the power x minus, okay, 1 by 6x. So now if you put x is equal to 0 here, you will get so this is in the form 0 by 0 again, okay. So we need to differentiate it once again. So limit x tends to 0 f triple dash x by g triple dash x, so e power x by 6. So now this is, if you put x is equal to 0, now this is 1 by 6, which is not indeterminate form. So 1 by 6 is the right answer. So we kept differentiating fx and gx separately with respect to x until the indeterminate form is removed, okay. So we got either a real number or infinite or minus infinite as the limit. So next is indeterminate form 2, second indeterminate form 2, which is 0 into infinity. So this is also indeterminate form. So this form can be easily reduced to the form 0 by 0 or infinity by infinity. And then L'Hospital's rule may be applied, okay. So like, so convert to 0 by 0 or infinite by infinite form, and then apply, then use L'Hospital's rule, okay. So if you can say, we can write this as, if limit x tends to a, fx dot gx is in the form 0 into infinity. So what you can do is, you can write this as limit x tends to a, fx by 1 by gx, okay. So now this is in the form 0 by 0, or so this is in the form 0 by 0, or you can write this as, if this is 0 into infinity, right, if the limit becomes 0 into infinity, so, or you can write this as, convert this to infinite by infinite form, like, so gx by 1 by fx, so this is infinite by infinite form. So now you can use L'Hospital's rule. Next is form number 3. Form 3, which is 0 raised to the power 0 or 1 raised to the power infinity or infinity raised to the power 0. Okay. So in this case, suppose we have limit x tends to a and fx raised to the power gx. So now taking log on both sides, we have, if this is y is equal to, so log y is equal to limit x tends to a gx log fx. Okay, so now this is in the form 0 into infinity. So you can convert this into 0 by 0 form or infinity by infinity form. Then you can use L'Hospital's rule. Let us understand this with an example. So if we have to find limit x tends to 0, 1 plus 2x raised to the power 1 by 3x. So this is in the form 1 raised to the power infinity. So this is form number 3. Okay, taking if this is y, so taking log on both sides, 1 by 3x log 1 plus 2x. Okay, so now this is in the form log 1 is 0 by 0, so this is in the 0 by 0 form. So now using L'Hospital's rule, so differentiating log 1 plus 2x is 2 by 1 plus 2x, and differentiating 3x with respect to x, which is 3. So we got, if you put x is equal to 0, so you will get 2 by 3. So log y is 2 by 3, so y will be e raised to the power 2 by 3. Okay, so e raised to the power 2 by 3 is the answer for this question. Okay, so next is continuity. Continuity. A function fx is defined for x is equal to a is said to be continuous fx is a function fx is said to be continuous at x is equal to a if the limit of the function limit of fx as x tends to a exists and is equal to the value of fx at a. Fx at x is equal to a. Okay, so the function is continuous at x is equal to a if we have f of a plus 0 is equal to f of a minus 0 is equal to f of a, otherwise it is discontinuous at x is equal to a. Okay. So or limit x tends to a, you can write fx is equal to fa. Yes or no? So And also this should be the value of fx at x is equal to a should be a definite number. Okay, so next is continuity in an open interval. So this is written as continuity in an open interval it is written as a comma b. So if it is continuous at each point of open interval except a and b, so this is continuous in an open interval. And continuity in closed interval, so you can write this as close bracket a and b. So if it is continuous from the right at a and continuous from the left at b, okay, and continuous on the open interval a comma b. Next is few standard continuous functions. Okay, so first is x power n is continuous for all x when n is greater than 0. For example, x square, x raised to the power 3, x raised to the power 2 by 3, 3 by 2. Okay. Second is x raised to the power n is continuous for all x except at x is equal to 0 when n is less than 0, that is x power minus 2, x power minus 1, x power minus 3. Okay, so this is 1 by x squared, 1 by x and 1 by x cube. Next is modular x is continuous for all x and then log x is continuous for all x greater than 0. And every exponential function is continuous, like ex, a raised to the power x is continuous. Next, sin x and cos x are continuous function. Sin x and cos x are continuous for all x. Then tan x and sec x are continuous for all x except at x is equal to 2n plus 1 pi by 2. Then cot x and cosec x are continuous for all x except at x is equal to n pi. So let us see one example. So find continuity at x is equal to 0, and the function is 1 by 1 plus 2 power 1 by x. So let us check the left hand limit. Limit s tends to 0 minus f of 0 minus h is 1 by 1 plus 2 1 by 0 minus h. So which is 1 by minus h. So 1 by 1 plus 2 power minus 1 by h. So if h is 0, then 2 power minus infinity, which is 0, so 1. Okay. And limit h tends to 0 plus, or right hand limit f of 0 plus h is equal to 1 by 1 plus 2 by 1 plus 1 by 0 plus h. So where h is 0, so 2 raised to the power infinity, so which is 1 by infinity, and which is 0. So see, left hand limit is not equal to right hand limit, hence fx is discontinuous at x is equal to 0. Okay. So next is differentiability. A function is said to be differentiable if limit h tends to 0, f of x naught plus h minus f of x naught by h and limit h tends to 0, f of x naught minus h minus f of x naught by minus h. Okay, so where h is greater than 0, so this is right hand differentiability, and this is left hand differentiability. So if these two are equal and they exist and they are equal to f dash x naught, that is limit x tends to x naught, f of x minus f of x naught by x minus x naught. Okay, so if these three are equal, then we say that fx is differentiable at x is equal to x naught, right? So if they exist finitely and are equal, then we can say fx is differentiable at x is equal to x naught, right? So note that continuity is a necessary but not sufficient condition for the existence of differentiability or finite derivative. Means if a function is differentiable at any point, then it is necessarily continuous at that point. Okay, but converse of this is not true. Okay, converse of this is not true. There are few standard results in differentiation too. So here they are. So I will upload this notes on my Telegram channel. So you may find the link in description box below. Okay. So let us see some examples. So find whether the function is continuous and differentiable at x is equal to 0. Okay, so fx is minus x cube by x for x less than 0, for x less than 0, or this is minus x square. Okay, also it is x cube by x, which is x square for x greater than 0. Okay, so this is at x is equal to 0, left hand limit is equal to right hand limit is equal to f of 0. Yes, then that means this function is continuous at x is equal to 0. Right? Now let's check the differentiability. So f dash x is minus 2x for x less than 0 and plus 2x for x greater than 0. So at x is equal to 0, limit x tends to 0 minus f dash x is equal to limit x tends to 0 minus 2x, which is 0. Also limit x tends to 0 plus f dash x is limit x tends to 0 plus 2x, which is again 0. Okay, so left hand differentiability is equal to right hand differentiability. That means the function is differentiable at x is equal to 0. Okay, now let us see the second question. So find continuity and differentiability of function at x is equal to a, where function is x minus a sine 1 by x minus a, where x is not equal to a, or 0 x is equal to a. So for left hand limit, we have limit x tends to a minus x minus a sine 1 by x minus a, which is 0 sine 1 by 0. So 0 into sine infinity. See, sine x varies between -1 and +1. So sine infinite is a finite value. So again, right hand limit x tends to a plus x minus a sine of 1 by x minus a which is 0. So this is again 0. So here also fx is 0 at x is equal to a. So this function is continuous at x is equal to a, since left hand limit is equal to right hand limit. Okay. Right hand limit is equal to f of a, that means continuous at a. Now let us check the differentiability. So for right hand differentiability, we have f of limit h tends to a, f of a plus h minus f of a by h. So this is limit h tends to a. Okay, so a plus h minus of a sine 1 by a plus h minus a and minus f of a which is 0 by h. So this gets cancelled. So this is h sine 1 by h. Okay. So limit h tends to a is sine 1 by a. Okay. So now for left hand differentiability, limit h tends to a, f of a minus h minus f of a by minus h. Limit h tends to a, so a minus h minus a sine 1 by a minus h minus a minus of fa which is 0 by minus h. Okay, so this gets cancelled again, which is minus h sine 1 by minus h and minus h. So this gets cancelled. So we have sine 1 by minus h, and this is okay, sorry, I have taken a everywhere. So h tends to 0 now. Zero. Here 2. Towards 0, 0. Right? So sine 1 by h, which is sine 1 by 0, which is sine infinity, and and here sine 1 by minus h is sine of minus infinity. So which is not equal. Okay, obviously sine infinite is a finite value between minus 1 and plus 1, but even the sine of minus infinite is a finite value, but we can't say that they are equal. So this function is not differentiable at x is equal to a, since left hand differentiability is not equal to right hand differentiability, so not differentiable. Okay. Next is mean value theorems. Okay. So first is Rolle's theorem, Rolle's mean value theorem. So if a function fx is such that fx is continuous in closed interval a and b, okay, or you can write this as, so next condition is if f dash x exists, means fx is differentiable in open interval a comma b or a to b, and third condition is if f of a is equal to f of b, then there exists at least one value of x, then there exists at least one value of x, say c, where c lies in between a and b, so such that f dash c, or differentiation of f of x at c, is equal to 0. So let us see geometrical interpretation. So if we have a curve fx such that, okay, at point A and point B we have the same value, so this is, say x is equal to a and x is equal to b, okay, and this is x is equal to c, so now, so let us find f dash c, that means slope of tangent line, this slope of a tangent line. So f dash c is nothing but slope of tangent so which is equal to slope of AB, because they are the AB and this line are tangent, are the parallel lines. So you can say y2 minus y1 by x2 minus x1. So f of b minus of fa by b minus a, or you can write this slope of AB line. So since f of b is equal to f of a, so this is 0 by b minus a, since f of a is equal to f of b. So we found that f dash c is equal to 0. Yes? Okay. Rolle's theorem asserts that there is at least one point lying between A and B such that tangent at which is parallel to x-axis. That is, there exists at least one real number C in A comma B, okay, such that f dash C is 0. Okay. There may exist more than one point between A and B, the tangents at which are parallel to x-axis. So let us see one more figure. Yes. So there may exist more than one real number C in AB such that f dash C is 0. See here, there are 2 points. Okay, so that means Rolle's theorem ensures the existence of at least one real number in C, one real number C in A comma B, such that, so Rolle's theorem ensures the existence of at least one real number C in open interval A comma B such that f dash C is 0. So Rolle's theorem fails even if one of the three conditions is not satisfied by the function. See, if first condition was, so first condition is fx is continuous in closed interval A and B. F dash x exists means fx is differentiable in open interval A comma B. And third condition is f of A must be equal to f of B. Okay. So the converse of Rolle's theorem is not true. Okay. So let us understand this with an example. So let us say we have fx x square minus 1 x minus 2. So in closed interval minus 1 2. So since fx is a polynomial function, since every polynomial function is continuous, so this is continuous in minus 1 comma 2. Okay, first condition satisfied. Second, so fx, if fx is a polynomial function, it is derivable, right? So next, check the condition f of minus 1, which is 0, and f of 2 is 4 minus 1 3 into 0. So all the three conditions for Rolle theorem are satisfied. Therefore, there exists at least one real number C in -1, 2. So we have, let us find f dash x, which is x minus 1 x square minus 1, and this is in the u into v form. So x square minus 1, differentiating x minus 2 with respect to x, which is 1, okay, plus, so x minus 2, and differentiating x square minus 1, which is 2x. So we have x square minus 1 plus 2x square minus 4x. Okay, so 3x square minus 4x minus 1. So since f dash c is 0, so f dash c is, replace the value of x with c. So 3c square minus 4c minus 1 equal to 0. So solving for c, you will get 2 plus minus root 7 by 3, right? So now, so also, so this 2 minus root 7 by 3 and 2 plus root 7 by 3, both lies in between -1 and -2, -1 and 2. So there are two real numbers such that, two real numbers in open interval -1, 2 such that f dash c is equal to 0. Okay, so we got two real numbers. So hence Rolle's theorem is verified. Next is Lagrange's mean value theorem. Lagrange's mean value theorem. Okay. So if a function fx is first continuous in closed interval or second fx is differentiable in open interval, okay, and here f of a is not equal to f of b, okay. So then there exists at least one value of c, then there exists at least one value of c in the open interval a comma b such that f dash c is equal to f of b minus f of a by b minus a. Okay, let us see the geometrical interpretation. If we have a curve like this, see, this is A and this is B. See, so x is equal to A and x is equal to B. Okay, so slope of the chord AB, slope of chord AB is equal to f of b minus f of a by b minus a. And since this tangent and the chord is parallel, so slope of this tangent at C is equal to f of b minus f of a by b minus a. There may exist more than one point between A and B, the tangents at which are parallel to the chord AB. Let us see this geometrically. Let us see this as A, this is B, this is P1, this is P2, this is P3, this is chord AB, this is at x is equal to A, this is at x is equal to B. Okay. So Lagrange's mean value theorem ensures the existence of at least one real number C in AB, open interval AB, such that f dash C is equal to f of B minus f of A by B minus A. That means there may exist more than one point between A and B where the tangents at those points are parallel to the chord AB. And yes, converse of Lagrange's mean value theorem may not be true. Let us see one example. Fx is equal to log x in closed interval 1 comma e. Since log x is continuous for all x greater than 0 and log x is defined for all x is greater than 0 and it is everywhere differentiable. Okay. So now f of e is equal to log e and f of 1 is equal to log 1, that is 0. So now and f dash x is equal to 1 by x or f dash c is equal to 1 by c and 1 by c is equal to log e minus log 1, so which is 0. By e minus 1, so which is log e by e minus 1. So c is equal to e minus 1 by log e. Okay, since this is base e, so this is e minus 1, 1. So answer is e minus 1. And obviously this lies in between open interval 1 and e, since e is equal to 2.71, approximately 2.71. Okay. Okay, now next is Cauchy's mean value theorem. So let fx and gx be two functions defined such that f and g are continuous in the closed interval ab. Second, f and g are differentiable in open interval a and b, and also g dash x is not equal to 0 for all x belongs to a comma b. Then there exists at least one value of c in a comma b, okay, such that f dash c by g dash c is equal to f of b minus f of a and g of b minus g of a. Okay, there are some standard results on continuity and differentiability of commonly used functions. Okay, some important results. So any polynomial function is differentiable everywhere and obviously continuous everywhere. Okay. And continuous everywhere. Exponential function like ex, ax, etc., sin x as well as cos x are also continuous and differentiable everywhere. Log function, logarithmic function, trigonometric function and inverse trigonometric function are differentiable within their domains. Within their domains. Yes. Next, tan x is discontinuous at x is equal to plus minus pi by 2 plus minus 3 pi by 2. Okay. and so on. Mod x is continuous but not differentiable at x is equal to 0. Okay. If f dash x approaches to plus infinity or minus infinity as x tends to k, then function is not differentiable at x is equal to k, right? Okay, let us see one example on Cauchy's mean value theorem. If fx is given as e power x and gx is given as e power minus x in a comma b, right? So fx by gx is equal to e power x by e power minus x, right? And f dash x by g dash x is equal to e power c by minus of e power minus c, which is equal to e power b minus e power a by e power minus b minus e power minus a. Okay. So you can write this as e power b minus e power a by e power a minus e power b by e power a plus b. Okay. So which is equal to, so e power 2c is equal to e power minus e power 2c is equal to minus e power a plus b. Okay. So which gives c is equal to b plus a by 2. Okay. So and yes, a plus b by 2 lies in between a and b. Okay, so let's wind up here. We will see applications of derivatives and maxima and minima in the next lecture. Till then, keep preparing. Thank you.